And the title of the talk is Efficient Algorithms for Planning with Participation Constraints.
Hello. OK. So thanks for the introduction. It's joint work with Cheng, who's moving to Brown as an assistant professor, and Vincent Conitzer, who's moving to CMU. Right. So you got 5 minutes. So I'll try to just sell you the problem and briefly mention the results. So it's a principal agent model. And to set up the model, let's consider the following scenario. There's a customer who's negotiating a plan with a phone carrier. So here's what the carrier offers. The customer pays $10 per month in the first year and $20 per month after that. And moreover, in the first year, if the customer decides to walk away to switch to another carrier, then there's a one-time early termination fee of $100. So the customer's problem, the decision problem, is then MDP, right? So for example, in the first year, the MDP looks like this. In state now, there are 2 options or actions that the customer can play, right? The customer can walk away right now, don't sign anything, and the procedure terminates. Or the customer can sign the contract, pay $10, enroll the service, and we move forward to month 1. So in month 1, there's again 2 actions, and they are kind of similar, except that if the customer decides to walk away, then there's the early termination fee. Well, after the first year, the MTP becomes kind of different, but the idea is the same. So there's many factors here, but it's an MDP. MDPs are easy to solve. So here's how the customer reasons about it. The customer likes AT&T, so $10 is OK. 20 is a bit too much. Another factor, if the customer switches to another service, to another carrier, that's great too. So there are outside options. And moreover, the customer definitely doesn't want to pay the early termination fee. So given these, maybe the most reasonable decision for the customer to make is to stay in the plan for exactly 1 year and quit right after that. So that's what the customer does. And after 1 year, the customer walks away. Well, that's not the most ideal situation for the carrier. So the question is, what should the carrier do? Right? And that's the question we try to answer in this paper. If the carrier becomes like fully serious about the problem, they will realize that this problem, the carrier's problem, is also an MDP. But the subtle point is the carrier has additional participation constraints because they want the customer to stay in service. So that means the customer's onward utility at any moment during the service has to be at least as good as the best outside option. That's what keeps them around. So now I can get a little bit more formal. So here's the environment. Looks very much like in standard MDP. So we have finite state space S, finite action space A. There's transition probabilities. P of SAS prime is the probability that I go to S prime and I play A in state S. Pretty standard. Assume there's no cycles, so you can only go from smaller states to larger states. And the difference is we have 2 reward functions. So it's a principal agent model, right? There's a reward function for the principal and another function for the agent, and they can be the same or zero sum or whatever, arbitrarily correlated. So that's the model. The computational problem we try to solve is given all parameters of the model, the transition probabilities, the reward functions, everything. We want to compute a principal optimal policy, one that maximizes the principal's expected reward, subject to the constraint that the agent's onward utility in each state is at least 0 or any constant. Doesn't really matter. So here we consider fully general policy is history dependent and randomized. And the reason that we do that is you can show that the optimal policy generally needs to be history dependent. And we don't want to be suboptimal, so we have to be history dependent. And here's actually one instance where any history independent policy is terribly suboptimal. Probably don't have time to explain it, but the idea is in the past, the agent may randomly suffer or not suffer. And if they suffer, you want to compensate them in the future, right? But if you want to be history independent, you don't know the past, so you have to always compensate them in the future. And if it can be history dependent, you can compensate them when they suffer and exploit them when they don't suffer. Right? That's the idea. So here's our results. I've told you that the optimal policy may necessarily be randomized and history dependent. So that means the policy is generally exponentially large in the flat representation, right? So you can't compute that explicitly. So nevertheless, we give a polynomial time algorithm that computes the succinct representation of the optimal policy. And that's a polynomial time algorithm for the exact policy in the finite horizon environment. And that also implies an additive epsilon approximation in discounted environments, which runs in time polylog 1 over epsilon. I have a few more slides, and I wish I could explain them, but let me finish here.